how will you implement this? So now you design a controller, the adaptive controller as tau equal to y transpose theta dot theta hat plus kr, and y hat is a time variant signal that estimates the system parameters. And so you have to learn the dynamics is theta hat dot, and this is the is designed to be again times the regression matrix R, regression matrix Y and R, okay, the Turkian air signals. We call Y as a regression matrix. Regression. Okay. And this is filtered Turkian air. Okay. So you know the regression matrix, right? Which is this part, which is a function of the desired trajectory and the Turkian air E dot and some measurable terms Q, right? So everything here is known, so you can implement this. For theta hat is a time variant signal. It follows this dynamics. Okay, so to obtain this, you need to integrate this. Okay, you need to integrate the adaptive law of theta hat. Okay. You're trying to learn or adapt to the true signal. Trying to use this rule to learn the true parameters, although it might not eventually converge to the true signal. Okay. So the way to obtain this, so in your controller you implement this and this. Everything is known, right? But here we need to do one more step, which is you need to integrate this from 0 to t. Okay, given any initial conditions. And this is user's choice. Okay, you can put whatever initial condition you want and integrate this. Okay, 这样没有问题。Okay. So, in the block diagram, this is system, right? And it takes the input and generate the output, which is Q and Q dot. Okay, and here's the controller. Okay, it's trying to track some QD signal. Okay, and here's the feedback. Okay, here's the controller. Here. So the way to generate this tau is compute these two terms. Okay. So R again is the control gain you can select. R is the filtered Turkian air, which is you can do some filtered Turkian air here. Okay. Say R equal to E dot plus alpha E. Okay. So you can obtain E dot and E both from here. QD dot. Okay. Filter checking in. Tracking. Air. Okay. And in here, you have theta head, which is time variant. So you need to do this. Okay, one more block doing this. And this generates the updated theta head. And that's required for the controller to realize, to implement. Right? Okay? So the difference is, you not only have feedback, you have feed-forward term. And feed-forward term is coming from adaptive, coming from time-variant signal, which is updated according to the adaptive law. Okay? Adaptive law here. Okay? But for robust, you just do KR here, right? KR and plus K2R. And you don't need, it doesn't require theta head. Okay? That's the difference. And the benefit of introducing these terms give you the global asymptotically stable, which we're going to prove, okay, in the next few steps. So this is for control implementation. And here we say V is PD, but V dot is an SD, right? But you can use Barbara's lemma to show, use this evidence to show that R will eventually converge to 0. According to 6 and 1, we can show that both signal R and theta tilde are bounded, right? Because V is bounded, right? Because V dot is negative semi-definite, right? So V, the worst case, the largest value of V dot is 0, right? When R is 0. That means that V cannot increase. The worst case is V is hold at constant, right? It only decrease, either decrease or hold at constant. It never increase. That means that both signal R and theta head will be bounded. Okay, so both will be bounded. Across 1 and 6. Now you can apply Barbara's lemma to show R converges to 0 as t equal to infinity. So next slide, we call it signal tracing. So it starts from these two signals, which are bounded. Okay, V is bounded, so both signals are bounded. And because tilde is bounded, and this defined as theta tilde equal to theta minus theta head, and because it's a constant, if this is bounded, this will also be bounded. So theta head is also bounded. Okay. So what does that mean? That means that no matter what initial condition you selected, the integration of this term will remain bounded. Because this guy, the guy you are integrate, have Y and R signal, right? And both are time variant. If you are integrate something that is always positive, eventually will go to infinity. If you are integrate something that is time variant, Y and R, and it's hard to tell, you can use the above function, and do the signal tracing and give you that no matter how you integrate, this signal will remain bounded. If I just ask you, here I integrate some signal, right? From 0 to t, t goes to infinity. Okay, is it bounded? Because in the control, everything had to be bounded, right? We already show R is bounded. K is constant. So this term is bounded. Okay. And this term should be bounded. It's a function of error signal desired trajectories. Okay. So the questionable term is this term. Because if it's unbounded, control input will be unbounded. You cannot ask a system to generate infinite large control output, right? No real mechanical system or electronic system can do that. If you are controlling a motor, this is torque, right? You cannot generate infinite large torque, right? So that means that all these signals have to be bounded. And this is the way we show that it's bounded. Okay, it's hard to tell from here that if theta hat will be bounded, because you're doing integration here it's hard to tell, right? Because you are integrating some time variant signals. But using the above function approach, okay, we say based on 1 and 6, both signals will be bounded, right? And because this is theta tilde is bounded, and from the definition of theta tilde, this is constant, this is bounded. It has to be bounded, right? So now it's proven to be bounded. So you don't need to worry about the control output. 所以你不是直接看这个是bounded，你看到你毕业也看不出来，对吧？所以我们用另外一个方式来看 signal tracing 来看。We show it's bounded. What else? Because R is bounded. Based on the filter tracking error properties, both signals will be bounded. Okay, we showed that in previous week. Okay, you can check the definition for filter tracking error. So if this is bounded, both will be bounded. And here R is bounded, so both will be bounded. So this guy means he is uniformly continuous, right? Okay, uniformly continuous. And now you can check. So this is bounded, and this term, you need to check out this term. So this term is a function of Q E dot Q D double dot. Okay, why? Because based on the definition of regression matrix here, right? It has QD double dot, right? QD double dot. You have E dot and Q, E dot and Q. Okay. So is it bounded? You need to, if you want to check whether it is bounded or not, you need to check these three signals. And Q and E dot is bounded here, based on here, so it's bounded. Okay, it is bounded. QD is bounded because it's a user choice. Okay. QD is desired, this acceleration of desired trajectory. So you always design trajectory that the two times derivative will be bounded. Okay, so both will be bounded, and this for sure will be bounded because from the definition E equal to QD minus Q, and from here, right, it's bounded, and this is user's choice, which will be designed to be bounded. So this guy have to be bounded. Okay, so Y will be bounded. Okay. And therefore, tau will be bounded. And that's important. Okay? That's important. So do you see how powerful it is, the Lyapunov function is? Originally the problem was I give you open loop dynamics, right? MQ double dot plus blah 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 equal to torque, right? And you design torque as this. Okay? And remember, dynamics is nonlinear. You don't know the solution. You design adaptive control, okay? At that time, you have no idea whether it's bounded or not, but it is required to be bounded in practice, right? So you have no idea, right? So the next thing you need to do is to design the above function, take the time derivative, do the stability analysis, and eventually that give you all the signal transients, and you can check whether the signal you put in your control is bounded or not. Everything is on paper, on a paper and a pen, right? I give you a dynamics, a ODE, second order or first order. This homework is first order, right? Okay, and you can tell someone just by hand, by a paper, say the controller, the design of this will be bounded. Okay, and this is the way you show him, convince him that it's bounded. Okay, so this is how powerful the above function is. And next, we haven't done yet. We want to show that R will be 0 as t go to infinity. Okay, so we want to use Barbara's lemma. So using this closed loop dynamics equal to latch, and because every signal here, okay, is bounded, and m is a constant, so R dot had to be bounded. Okay, and for R dot to be bounded, R is uniformly continuous, and that's important to show that it's to use the Barbara's lemma. So next step, and remember the Barbara's lemma, the lemma says a signal had to be infinitely continuous and it had to be L2 function. And then you can show that you will converge to 0 as t equal to infinity. So you need to also find R is L2 function. Okay. So remember we show that V dot is NSD in the previous slides, right? NSD. And if you take the integration, you integrate both sides, you got Vt minus V initial condition equal to this guy. Okay, and this is bounded. This is bounded, and this is bounded, right? Because V cannot increase, it only decrease. So given some initial condition, this guy will always between this value and 0, right? Because P is PD and the largest value is V0. So this have to be bounded. Both will be bounded. So this means it will be bounded. And that says R is R2, L is a L2 signal, R is a R2 signal. Okay. So from R is uniform continuous and R is L2, we can show that R converges to 0 as t going to infinity. Okay, this is Barbara's lemma. So we show control is bounded, R converges to 0 as t go to infinity. Okay. And I know some of you might not believe this. That's why in our next homework, I ask you to do a simulation for second order systems. Okay. And one of the controllers is adaptive control. Another one is robust control. So you need to implement this controller and show whether the control input is bounded or R converges to 0. For a summary, adaptive control, the control structure is this. Okay, and you need to estimate the theta hat, okay, based on the adaptive load. And the result will be globally asymptotically stable. And for robust control, VR is the robust term and KR is the feedback term. Okay, VR is designed same as some constant times R, and the objective is to deal with the uncertainties or disturbances. Okay, so and you will get UUB. And you can by increasing the gains, the UUB ball, the steady state error can be decreased. Okay. OK， 所以这样 V 大会变什么？ND 吗？决定。你的 V 是什么？这样就好麻烦，还没结束。再来。
你这些白巴巴的。
Signal tracing 你要做啊，你等一下，你私底下来做。So yeah, that's right. Here is how we will do it. So I give you example. Say next slides. So everything is the same other than you just eliminate this. Eliminate this. Okay, then it's same as this. Everything below step 3 are the same because the difference in dynamics has been narrowed down, has been condensed in Y transpose theta, right? And everything remains the same as previous slides, okay? So in your controller is also different. The difference is Y transpose and theta, as well as theta hat. So you need to look into detail how step 3 to step 8 are doing. What's the strategies? If you have unknowns, how you can cancel the unknowns, or how you deal with unknowns, okay? And how you apply adaptive load to cancel out some terms here, okay? Theta, and because you are in your tau, you have Y theta hat that can be combined with Y theta, and that create Y transpose theta tilde. Okay, and this Y transpose tilde can be cancelled by this adaptive load. So basically, if you change the dynamics, okay, you need to do you need to cook the V dot, and somehow it becomes this form, okay, which is almost the universal form for adaptive control, okay. Because in this case, theta is a scalar, so you don't need to write. You can reduce to a scalar form, which is theta tilde squared and 1 over gamma, okay? Because gamma inverse is equal to 1 over gamma in the scalar case. So next, backstepping. So this is the general form of backstepping of some system, okay? Some higher order dynamic system. And the control we will use is backstepping for this type of dynamics. So you can see that typically we have one ODE, right? Here X is a scalar, okay, it's a scalar. And usually we put control here, but now control is at here, way far behind the first question. So we can imagine it's kind of like a high order dynamic systems. And how can you design controller for this one? Because if you design control, you only guarantee if you design the control you here, it guarantees you can control this YK signal to some desired value, right? Please turn in your homework on time next time, okay? Okay, so you only design this control only guarantee YK track is tracking some desired signal YKD. But what if the objective is to ensure X tracks some XD, the desired trajectories? How will you do this? Do you see the problem? This is the objective. Okay, you want to design control that ensure X track XD. So the objective is to design control enable X to track XD, but control is far away behind here. Okay, so how can you design you control this signal? Is quite impossible. 有了，对，谢谢。Okay. If I ask you that control design Y1 to track X, to enable X to track XD, that would be fine, right? But now I ask you, the control input is here, not Y1. Okay, so how will you do this? And in the first equation, you did not see control input U, okay? And second equation, you still not see control input U, and either Y3 or Y4, because your U controls YK, and YK did not in the first equation, second equation, and etc. Okay, there's no U layer. Like in the previous adaptive case, right? You design V in the analysis, you put Y MR squared, and you take the time derivative, you got RMR dot. And this is the control axis, right? This gives you the chance to substitute your control input tau, right? This is how control input come into system, right? Remember, right? Today. The next step is design this. Okay, so control input appears in the second time derivative of Q. But how about in here? Control input appears in the case time derivative in the system here, right? Because YK dot equal to U. So it's far away, far behind the first equation, okay? So let me give you a simple example, the first order case. So the objective is we want X converge to 0 as t equal to infinity, and X is in here. However, this Y is not the control input U, okay? But control input U controls the Y dot, not Y, okay? X dot equal to Fx plus G X Y, okay? And Y dot is U. This is not U. U is in here. And there's one more time derivative. Okay. Or you can combine it into you take one more time derivative on the first equation that give you F dot X. You can do this. And this is U. Okay, so U appears in the second time derivative of X. Okay, but what if a more complicated case where you have maybe x1 blah 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 and to xk, and that gives you control u. That's more complicated, right? 懂吗? So the general form of the system can be described as this. Okay, and the controller to be designed, the approach is called backstepping. Okay. So this is the black diagram of the system. Okay, and here's the X, here's the virtual control input. Okay, and this the true control input coming into play here. Okay, so this is the plant, is the system. Okay, so this X dot, after we do some integration, X dot is here, right? X dot is here. Okay, and X dot equal to what? Is summation of two inputs, right? One is gxy, one is fx. So this is this, right? Okay, and how did you give? How did y come from? It comes from the control input u with the integration, right? You integrate y, you integrate u and get y based on this. Okay, so this is the system block diagram, and all this is called system or plant. Okay, and based on what you learned in your undergrad for the modern control theory, this is the output X. Okay, X, and sorry, this is the plant, right? Which is this, and you are designing controller here. Okay, 懂吗? This is this, and the input U is from the controller you design. Is the output of the controller you design, and you are trying to track some desired signal for X to track some desired signal. Okay, is that clear? So you have this part in your system. That's the difference. Okay. 有没有问题? And here we assume gx is greater than 0. Okay. So this is system 1. System 1 is the first equation. System 2 is the second equation. Okay, and the overall system, which you combine the two equations, becomes one new system. Okay, and that's the system you need to control. Okay, and we call it cascade system. 串在一起, okay? Cascade of two systems. So how you design the control? How will you design the control? So let's look at the system by system. So first look at the system 1. We consider Y as a virtual control, not a true control. Okay. So we design a desired trajectory for y to track. Okay. So if you consider y as a virtual control, let me ask you a question. If this is y, if this is u, y becomes u, how will you design the system? Exact model knowledge. And this is greater than 0. Exact model knowledge. So I believe you will design u as 1 over greater than 0. It cannot be equal to 0. Okay. And what? Fx minus f to cancel all this, right? And a feedback term minus kx. Right? 对不对? With exact model knowledge. And this is feedback linearization. 对不对? However, it's not u, it's y. Okay, so I change u to be yd. Okay, yd. Okay? Maybe you're confused by yd. So let's say y, okay? It's fine. Let's say it's y. Okay? And you are done, right? You design a signal. If y can be this function, oh, that's great. X, eventually x, given any initial conditions. Given any initial condition, x 0 equal to maybe 3, whatever. Okay, and x will converge to 0 as t go to infinity. Right? Start from 3, it will converge to 0 as t go into infinity. 对不对? 对不对? 这没问题吧? Okay. Okay. If you agree with this, that's okay. So next, although I put yd here, but just forget it. Just think about y. Okay. So next, the second system is y u, and this is the true control you can design. Okay. So what will you design u? And now your objective is what? You want to control y to be some signal, right? You want to track y to be this y, right? So how, but what you can control is y dot, not y, right? Control y dot or control y are two different stories, 对不对? 懂我意思吗? Control acceleration is different to control position. They are different stories. So there's a gap between here and here. Right. This is my, so you can consider this as my desired trajectories. If I say, okay, and your initial condition is maybe 10, okay, or maybe 8. And that 8 is not, and here you have some condition x equal to 3, right? You put 3 into here, you got some value. which is not necessary to be same as the y initial condition there， 对不对？对吧？两个不一定一样嘛，懂我意思吗？ You want to that y to be this value, okay? And you substitute your initial condition of x, the y will be some value. But that value might be different from the initial condition here. 对不对？听懂吗？ Okay, so you cannot put y here. You can consider y as a desired trajectory you want to track for that system. 懂吗？ Because y can be any initial condition. And that initial condition might not be same as the desired value of this system. 能懂吗？能懂不懂？懂吗？不懂，懂。这边没有问题嘛，对不对？所以给定一个 x 初始值，我的 y 值是不是就固定了？但是在那个 system 的 true system 里面 ，y 可以不是这个值啊，对不对 ？y 可以是任意 initial condition 嘛，所以是不是有个 gap？ 你怎么去弥补这个 gap？ 你就把 y consider as a yd，OK？、And this yd is the desired trajectory for this system to track. So in this system, the objective is for control y to track yd. And if that objective is achieved, it guarantees x will also converge to 0. 你懂吗？懂吗？ So now, use the objective. How will you design the controller? It's a tracking problem, right?这边懂吗？这边是要给定一个 y 的 trajectory 嘛？但是你可以控制的是 y 吗？你可以控制的是 y dot 吧？对不对 ？Here is asking for yd, but here you cannot control y. What you can control is y dot. Control y dot is different, totally different from controlling y. Control acceleration is different from control position, right? Here is asking for an exact position trajectory. Here, you cannot control position, you can control velocity. And if you are not initially at the position that is required to stabilize the system here, you screw up, right? So you can change the problem to be a tracking control problem. I don't ask you to initially locate at the exact location as required by the system one. Okay, it's not required, but eventually they will be, right? Eventually, this y will be yd. 听懂吗？听懂吗？ Okay, so that's a tracking problem. Here's a regulation problem, and this yd is a virtual control. All you need to do is design u. 听懂吗？ Because u is the physically exist, not y. Okay. So the system is y. Okay. And if y achieve yd, if y track yd, x will converge to 0. Okay. Okay. So, how do you design the control? So let's analyze the first system here. Okay. First, I define, we know that YD is the virtual control and the desired trajectory is this. And we define a signal eta that is the difference between YD and Y. Okay, and that's the tracking error for the second system. Okay. And now in the system 1, x dot is equal to f x plus gx y. Okay. Now I subtract and add. Okay. I subtract and add the same term, which doesn't change the dynamics. Right? Next, I combine these two. That give me what? That gives me, okay, yd minus y. That's fine. That give me gx times eta. Okay, plus gx yd. Okay. All the step here I do is trying to convince you that designing YD as this, designing the virtual control YD as this, can ensure X will converge to 0. Okay. Here we can consider as a stability analysis, and we want to find the virtual control. Okay, because I already told you the answer, but basically the step here is trying to find the virtual control. Okay. So here is the open loop dynamics, and now we can substitute the virtual control input here to get the system 1 and open loop dynamics. Okay. Now we substitute the virtual control by in that form, you can obtain the closed loop dynamics. Gx times we substitute the control into here. Okay, you got what? Minus kx minus fx. Right? So this cancels out, and that gives you gx times eta minus kx. OK， 这样没问题。好 ，close loop 就到这边 ，OK。 Okay, so that's the closed loop dynamics for the first system. Now we go back to here, and the open loop dynamics is this. YD. Okay, so open loop dynamics for the tracking problem. It's a tracking problem, right? So the open loop dynamics is eta tracking control. So we want eta goes to 0. Goes to 0. Okay. Then eta dot, we need to take the time derivative. Eta dot is y dot minus yd dot. So that's control u minus, what is yd dot? Yd dot is this. Okay. Let's just say yd dot for now. Okay. Now by that design, so the controller is designed as this. Okay, this is the design. So we have designed two controllers. We have designed virtual control and the true control which is physically exist. Okay, this is the one you need to implement, but this is virtual control. Okay, just as an auxiliary term. So we design as this. You can substitute. You can use that u here. If you substitute u into here, you got yd dot minus k2 eta, which is feedback term, minus gx x. Okay. Minus yd dot. Okay. This will give you, and this cancels out. Okay, this give you minus k2 eta minus gx x. Okay, ma? So now we have two closed loop systems. This is yd, okay. After you substitute control u is closed loop systems. Okay. So you have two controls for each system. You have two closed loop dynamics for each systems. Now you can do the stability analysis. We design as a PD function, which is a function of x and eta, okay, which is a function of x and eta. Because you want x goes to 0, you want eta goes to 0, okay, and you take the time derivative of v, you substitute the both closed loop dynamic, you get v dot is negative definite. And that says x will converge to 0, eta will converge to 0. And you can use signal tracing to show both control u will be bounded. So the problem is how you design this and how you design both controllers. Basically, this term is a cross term. Okay, cross term means it cancels out with this. They are the same, but when you substitute into the diagonal function, they become the same because here it has 2 times, you have another x in front, okay? You have another x. The 4 is not big enough. Let me just keep this. Okay, closed loop system, or the first system, and closed arrow system, or the second system, which is eta dot equal to minus k2 eta minus gxx. Okay, then I can erase this, and let's do the diagonal function analysis, which is v equal to half eta squared. You take the time derivative, you got this, and you substitute the closed loop dynamics. Okay, gx eta minus kx plus eta times minus k2 eta minus gxx. And these two are the cross terms that can be cancelled because you have x in front of the term. You have eta in front of the term. Okay. And that's why it's called cross terms. Okay. So it's reasonable that the design of this cross term in the controller is based on the stability analysis. Okay. But for teaching, I need to first define it. I first need to give you the controller design such that you can follow the flow, this analysis flow. Okay. But when you design the controller, you need to go backwards. You need to probably go into the stability analysis and complete the design later. Okay. So in the controller, you have feed-forward term, yd dot, which is feed-forward, is the information of the desired trajectory. Second term is the control feedback, minus k error signal. And this term is the cross term. Okay. So you have 3 different terms for 3 different purposes. And in here, you just do the way, as I told you, the feedback linearization. Okay. But it cannot be y. Okay. It had to be yd because y might not initially be yd. Okay, and you are control y dot, not y. Okay, because your initial condition can be random, and this initial condition might not be this y, might not be the same y, might not be the desired same y. Okay, so you need to do a tracking problem that controls y to track this yd signal. Okay, and if y and yd are converging to the same, they have no difference, then x will converge to 0. Or in this first closed loop system, you can see that if eta, which is the difference between y and yd, is 0, if the difference is 0, this term will go away, right? So it becomes the closed loop becomes a linear feedback system today. Okay, but if it is not exist, this term will exist. But based on the stability analysis, v dot will be negative definite because this term will cancel out this term. Although this term looks like a bad term, but it will be cancelled by the second system. And if you don't design this cross term in your control, this term will be considered as a bad term, and it will remain in the system, and that prevents you to get a globally asymptotically stable. So this is a simple first order case, and probably I will give you, we will mention a higher order case in the future.